Before getting into some of your work history, can you tell us a bit about what about your life before you arrived at Chalk River?
Well, I was at school, of course. When the war started, I was 9 years old, and we were evacuated into the countryside, away from London. And there I received my schooling in two schools, an elementary school and a grammar school. The grammar school was evacuated close by, which is very convenient for when I was 11, that move. And it was a big, well-run campsite with 200 boys needing to be looked after. And I was 5 years there, and we all came back to London after the war and settled into the old school in London, Camberwell. And there I completed my grammar school education. And after that, I was looking for a university seat, but there were none to be found. And I had a very capable sister, who was 5 years older than I was, who worked for UNRWA, the United Nations Relief Organization, and they had a cricket team, and they were short of players. And I was playing a lot of cricket at that time, and she asked me whether I could help out, so I did. They happened to be playing a team from the research laboratories of the General Electric Company in North London, and they had a program there where you could be a student assistant and study part-time at London University for your degree. It was a very useful program and well run, and didn't cost me a cent. So I was very lucky to be hired by the laboratory and worked in a graphite laboratory, working on carbon and graphite. And the laboratories themselves was a huge collection of different disciplines, from fluorescent lamps to refrigerators to carbon because General Electric were interested in carbon arc lamps and the carbons which were used in them. So the carbons themselves, which are long rods, had to be quality controlled and made sure they were strong, that they wouldn't break when the arc lamp was running and stuff like this. So the carbon laboratory was very interesting, and I fortunately became adept to many aspects of the work in the lab, which was a real education and held me in good stead later. I learned how to use a lathe, learned how to do this, learned how to do that. You had to, because the job had to be done.
Yes.
There's nothing proud about it, just had to be done. And then I saw in a newspaper an ad from Atomic Energy Canada Limited looking for metallurgists, or metallurgists. And my wife and I were living with her folk, and we both thought it would be nice to emigrate to Canada. So I applied for the job, and a Mountie arrived in the neighborhood checking up on our social behavior, make sure we weren't wild things.
A Mountie visited you?
A Mountie, oh yes.
In London,
he didn't bring his horse,
yeah.
but it was a Mountie. And then we heard that my application was being looked over, and would I attend an interview downtown London with one of the divisional directors, Dr. Bill Campbell, who directed the metallurgical division, I think it was called at that time. And he was very, very nice to me. And I got an offer for a job which doubled my salary. And the administrative assistant here, Hugh Longfield, wrote us a long letter telling us what things cost, and reassuring us that we would be very welcome and that we would manage. By that time we had a young baby, a young daughter, so my wife was particularly concerned with living conditions in Deep River. By that time in 1957, things of course were well established here, and we were assigned an apartment with 2 bedrooms. From living in a one room with our in-laws to having an apartment with 2 bedrooms was just heavenly. And that's how we began our life here. It was a little bit of heaven, really. little bit of heaven.
That's a very interesting history, and so one might say, in some ways, cricket brought you to Canada indirectly.
We didn't finish. We played cricket here.
With an application, yeah, yeah. So you arrived in '57 then.
57 years.
'57, and those were busy days of material science, metallurgy, materials development, a lot of research and modeling going on. What were some of the things you worked on initially, and what were some of the challenges?
Well, my boss was going to be Jeff Chalder, and he put me to work in getting a literature survey on the general properties of uranium dioxide. There was not too much around because I think the use of the U.S. Navy in developing reactors for their submarines meant that a lot of information would not be disseminated. But in the literature, at least, there was information available because other countries were using UO2 as well. So that literature survey started me off being I knew that I was going to be not sent home. I had the feeling that you're on probation, Alan. You do a good job. But as it turned out, that was okay. And I got to be introduced to uranium dioxide as the fuel for that we were supposed to be working on. The main problem, it seemed to be, was to satisfy Dr. Lewis's request that the fuel itself should be as dense as possible so that he could have a minimum effect on the core volume. A dense fuel meant a dense core. It had to be big, of course, because of the heavy water natural uranium physics, but at least we had to produce fuel pellets that were good and dense. The Americans were using porous fuel pellets because they were worried about swelling. They thought the porosity would cope with any fuel swelling.
Accommodate the swelling. Yeah.
Yeah. But in their tests, the fuel pellets were in a vertical stack, and the radiation caused the pellets to shrink, the stacks to collapse a little bit, and so the cladding itself would become unsupported. So they're having all kinds of failure problems because of their choice of porous UO2. That's how I read the literature. We didn't know too much, of course, sure, but that's how I regard their problem with UO2. Our problem was just the opposite. We were trying to produce a good, dense, hard pellet that wouldn't flake, wouldn't break up too much, and all this stuff. And our fuel columns were, of course, horizontal, or were going to be horizontal in the reactors, but all our tests on the fuel pellets were mostly metallographic, looking at their structure, understanding the sintering process, which was a bit dicey at times because the UO2 arrived for our use as a fluffy powder. And a fluffy powder is sometimes difficult to control. And we had to get this powder into compaction dies. Mm-hmm. And a fluffy powder, you couldn't get too much in. So we looked at a process called pre-pressing. The fluffy powder was pre-pressed into slabs. The slabs were then ground up, and a granular powder was formed from that. A bit like, a granular powder instead of a fluffy powder.
Yes.
And this granular powder would pour easily into the opening of a die, and you could pour it in a controlled manner. And at that stage, we also introduced the use of lubricants, just a little bit of lubricant, mainly a stearic acid or stearate compound, which would help the granules themselves slide over each other during compaction. That burnt off during the firing process. So there were two things: the pre-pressing method, how far you should go in pressing it, the process you should use for chopping it up, and addition of lubricant. Once we had that sort of sorted out, we prepared many pellets and made sure that we could understand the sintering process, so that the sintering process, which was done by putting the pellets in a molybdenum tube furnace and heating them to around 1700 degrees centigrade, understand that that sintering process would go not to completion. We could never get rid of all their porosity, but to get to a good high density, 95%. The theoretical density of UO2 is around 10.96, and we got up to sort of 10.5, and that was that target was met. So my work on in those days was largely worried about density, and it was a very nervous time because we had to achieve that, and we had to achieve with different powders that came from El Dorado in Port Hope as a product, and so their controls were a little bit variable. So we had to cope with powders that contained a little bit of excess oxygen. The composition of the powders was just not UO2, but UO 2.1, 2.15. And so we would sinter the pellets in hydrogen, which would reduce the, get rid of the oxygen, and reduce the pellets to stoichiometric UO2. We wanted to understand, though, the effect that the little bit of oxygen would have on things like thermal conductivity and about the metallography. So that was one, and how it would affect thermal conductivity. So I built a little apparatus, one of the first ones I built, to be able to carefully oxidize the pellets, which would start out as being UO2, sintered UO2 pellets, to different levels of oxygen. That would have to be done at 1000 degrees centigrade, according to the phase diagram. And I hung the pellets on a beam, and one end of the beam had a spring, which we obtained from the UK, and the springs were available in different strengths, so that I knew the weight increase that would be involved in adding oxygen. I chose the spring so that it would deflect, say, half a centimeter. And we viewed the spring through a vernier microscope so that we could measure the weight increase of the pellet hanging in the furnace, stuff like that. So we had a vacuum system to evacuate the whole system and refill with, say, nitrogen, or we could do it in vacuum.
Okay.
So that was a way that we knew how to vary the oxygen content to look at different properties.
Very interesting, very interesting.
But the main thing was thermal conductivity. The whole problem of temperature distribution in the UO2 pellets, which are running so hot in their center, was important because of the effect that it has on the structure of the pellet, fission gas release, and the actual mode of heat transfer to the cladding, which is being used to, of course, heat up the coolant. So I used the NRX reactor, which had a self-serve ball system, a very elegant, simple ball system, where you could put your sample in the ball with a cobalt monitor to measure neutron exposure, and the ball would go into a self-serve facility, and the ball could roll down into a position nearer the in the thermal column, depending on position, and then it will drop into a known position, and for its exposure. Once exposure was finished, then the platform would be tilted and the ball would roll back down another hole to a shielded flask on the outside as a reactor, and could be taken away. The self-serve And the self-serve facility was used for so many things, for biological samples, for metallurgical samples. It was such a simple system. And we know there was no ever any trouble in how many operators at NRX using it. They understood it, and it was a very simple thing. So it was an excellent radiation facility, and we used it a lot. So I was measuring thermal conductivity by a very simple method, and I could tell that radiation was decreasing the thermal conductivity, but when these samples were then annealed, then that effect was removed. So it's a bit like getting rid of Wigner energy in graphite.
Yes.
As long as they were running hot, the radiation damage could be annealed. And that was very interesting. And the other thing at the same time was, what does porosity do? And we soon found out that if you had 5% porosity in a pellet, its thermal conductivity would be reduced by 10%, double the amount. And that was important in modeling, because a lot of assumptions were made if a thing was 5% porous, you would reduce things like thermal conductivity by 5%, but that wasn't necessarily the case. So we got into pore morphology, and a lot of metallography was done to try and explain this effect. That porosity and radiation and stoichiometry were three of the things which I put together in just a summary report on how these things affected UO2. It's kind of basic stuff, but it had to be done.
And that was published, that report was about 1960 or 59?
Yes, yes, I figured the date. It was just a report summarizing the effects of radiation, porosity, and stoichiometry.
So important basic information for the modelers, but
well,
to get that information you needed good samples and be able to produce pellets and
yes,
and irradiate them.
We were lucky in that respect that the UO2 behaved itself.
So who did you work with on some of that?
A lot of that work I worked with Paul Bertium.
Paul Bertium, yep.
And Dick Stout.
Richard, yes.
Those two mainly.
Yes.
In our system here, it seemed that professionals were assigned technicians. And Paul was the first one who was assigned to me. And we got on well. I spoke schoolboy French, and he spoke Canadian English. And he was so energetic. He was a whirlwind of energy. Dick Stout was more of a careful, precise person. And his skills came in very important later on when we had to develop ultrasonic drilling to drill little holes in UO2. In the metals we use for fine, you can use very fine drills, but ceramics, we had to investigate ultrasonic drilling, which is like a road drill hammering at the asphalt, but our frequency was ultrasonic.
Yes.
And with water fed into the hole, and gradually this drill bit, which could be 5/1000 inch wide, would sink into the UO2. That was important to prepare holes to put in thermocouples.
Yes.
To measure temperature distribution. And we did a lot of investigating what machines were available, what frequencies being used, the shape of the actual drill bit. And Dick did most of that work and produced an ability to drill anything in a ceramic, particularly UO2. That was a great achievement.
It was essential. And later when I worked, I also worked with Dick Stout, and
oh, yes.
And he was still drilling very complex geometries in fuel pellets for different in-reactor irradiations. So
he is a very capable guy.
Very capable, yeah. So that work on uranium dioxide, effects of essentially porosity and stoichiometry and irradiation on thermal conductivity then was written up in a report, and then a lot of that material then ended up in the very famous book, or at least in my reckoning, I call it a
UO2
famous
book.
book, Uranium Dioxide by Jack Bell
Yeah.
from Bettis.
Yeah, he was one of the
Atomic
many
Labs.
Americans who were in our teeth, gleaning us for information, and we were gleaning them. But he was a very nice guy, and because we were involved in the sintering process, we also got involved with Professor Kingery, W.D. Kingery, the Massachusetts Institute of Technology, who was helping them, I guess, in their sintering problems.
Yes.
So the three of us added this chapter to the UO2 book. I didn't feel at the time it was. I just felt it had to be done. We had the information, and they could have it. There was no secrecy, no holding back of anything, because we needed the expertise of Kingery on sintering. We needed to understand sintering,
Yes.
but we all were very cooperative in those days. It was a nice feeling.
Did you travel down to the States for some of the interactions?
Well, most of us in our group who were working on UO2 ceramics joined the American Ceramic Society, who had a nuclear division, and we gave papers there.
Yes.
And that was, conferences were held in all the various US cities, which was a very pleasant experience for me anyway.
Yes, yes.
I remember Chicago being so hot and he died, but so hot and humid. But there are other more pleasant places, and I could take my wife, and places like California and Philadelphia. We were very lucky to have that support from the company that would allow us to, first of all, submit an abstract to the organizers of the conference, have it accepted, and then know that our paper would be given at a particular day. We got a program for the conference, and we knew which day it was, and so this sort of thing. So we were very, very lucky to have friendly cooperation with particularly the Americans and anybody else who wanted information from us, and to have the ability to travel.
Yes.
And to attend conferences and listen to papers on all kinds of aspects of fabricating nuclear fuel, like handling powders, and particularly then at the same time was embedding nuclear waste in glasses. What were the glass leaching rates? What happens when the glass containers get corroded by groundwater? That was a big question, which stopped them using glass encasement as a disposal method. Things like that was thing that we wouldn't be normally concerned with, but the papers themselves were very interesting. Very interesting.
Do you recall many interactions with the Russians in those days?
Not with Russians, no, but with other people from France and Germany. I once tried to send a fellow speaker a reprint of my paper, but he was from South Africa, and I kind of got a gentle rap on my knuckles because South Africa hadn't signed the non-proliferation treaty, and so cooperation with them was a no-no. That's the only instance I remember of being told, no, you can't do that. Other than that, we spoke to everybody.
So there must have been some interesting conversations at the American Ceramic Society meetings discussing some of the developments or learnings around sintering and properties.
They were enthusiastic and eager for information, and it was always a pleasure to give a paper in front of them, because they asked intelligent questions, and you had to be prepared to get the right sort of technically based answer. It was another world, really, the world of conferences and interaction, with the world at Chalk River. You really were out on the limb there, and you were representing your company, and you tried to do a good job. I did get a Best Paper Award at one conference. It was in California, and Ross McEwen was with me. And what we were trying to do was to show where the uranium oxide went in a mixed pellet of thorium oxide, uranium oxide. We would only be adding small amounts of UO2, because that would be the driver fuel for breeding in the thoria. But metallographically, you couldn't tell whether it was dispersed okay, whether the uranium dioxide particles had clumped together. But fortunately, uranium emits alpha particles as it decays, and we used track etch radiography to first of all show bad mixing, and then show how we could get good mixing. The track etch method is to lay cellulose nitrate on a polished surface, and the alpha particles damage a track in the cellulose nitrate. You then etch the cellulose nitrate to form a pit in the damaged track, and the pit, of course, will scatter light, so you could use the cellulose nitrate as a negative to make a picture. They were usually colored red to help contrast, but by putting the UO2 into the thoria as U3O8, the extra oxygen, it would be removed by hydrogen eventually, but the extra oxygen seemed to encourage the mixing process, and the thoria UO2 structure as a result looked quite uniform just by using U3O8. It's just a simple step. But we could prove it by scanning the surfaces with cellulose nitrate film and then etching them using pictures. Try to use the track etch method for producing images of fuel elements, because if your detector contained boron and you laid your cellulose nitrate against it, then an image could be formed in the cellulose nitrate. But the problem was and because of that, because of the limited range of alpha particles, you would expect the edges in the image to be sharp, much sharper than the photographic method, where the image is produced in Kodak film. Right. That was true, but the contrast was the problem. The edges were sharp, but the contrast available was just not good enough. It's like having a sharp image but a very faint one. It's difficult to explain, but in film technology, the contrast and sharpness is highly developed. But cellulose nitrate is very limiting. All you have is an array of pits, and you're trying to produce an image by light scattering from there. So it was promising. The beauty would be that we could use detectors of Pyrex glass, which was so cheap. Detectors in the normal one of the things was dysprosium poured as a thin sheet. But if you use Pyrex glass, that would have been a big step, because Pyrex contains lots of boron, and you could have had them add more boron to increase the number of interactions. But by that time, I think I was getting ready to leave. It's just, I think it was, neutron radiographs were produced at several sites using track etch radiography. But to my way of thinking, they look pretty wishy-washy. They were more used for detection purposes rather than an imaging or size measuring purpose. We tried a scanning photometer, a contrast measurement, yes, across the images, and they were sharp, but it was just the contrast which was a problem.
When you when you went to those American, I guess it was the American Ceramic Society meetings with as part of the nuclear
Yeah, they had a
meant
nuclear division.
nuclear division. Did you find coming from Chalk River that you were respected, or was there a reputation that was
I didn't know.
inherent coming
Nobody
from Chalk
booed.
River in those days? There was a lot going on, of course, in many labs around the world.
Yes, that's right. There was just a spectrum of international people in the audience, and everybody was anxious to get information.
Sure. Yeah. Yeah. Interesting days.
As I say, I never got booed.
But you received the best paper award for the track.
At one time, yeah. That was
work. Yeah.
those pits that develop in cellulose nitrate are so beautiful. They're just beautiful, and I was so excited. And I had figured out that U-234 is, of course, a strong emitter of alpha particles. It has a shorter half-life than U-238, so the intensity of those particles are useful. And if you used enriched UO2, it always had like a contaminant of U-234, so you had a big source of alpha particles that you could use for detection.
Okay.
And we had alpha particle monitors all over the place in Chalk River, but
of course,
to use them in film was interesting.
So there's another related area of research that you published in the early 60s that was around the gap conductance model.
Mm-hmm.
Can you tell me a bit about that work?
Well,
and
temperature distribution in the fuel was all important. Archie Robertson in particular was, but it's so important, his use of KD theta, that little expression.
Yeah.
But the temperature drop between the fuel and the cladding, right at the edge, we knew it was there, but we didn't have numbers for the actual heat transfer coefficient between the UO2 surface and the zircaloy cladding. So we decided to measure it, but to do that we had to get a UO2 pellet and put zircaloy probes either side and pass heat down the column and measure the temperature distribution of down the zircaloy and along the UO2 pellet, and have thermocouples very carefully positioned as close to the surface of the UO2 as possible. It was because of this skill, Dick Stout's skill, and using soft platinum 10% rhodium thermocouples, which could be worked to be very thin rods pushed into the holes. I don't think we cemented them. It just was a very tight fit. Mm. But that method had to be done by a very skilled technician, and he did it. So we had to get into roughness, how roughness affected the gap conductance. You would expect if two rough surfaces got together, there would be a bigger temperature drop between them when heat is passed through them than you would do if the surfaces were smooth. Yeah. So we got some advice from National Research Council in Ottawa about putting numbers on roughness, because you need numbers for modeling. What's the number you can use when you measure roughness on a sample? What does the machine tell you in microinches? Mm-hmm. Stuff like that. So we were educated there, and we could do different roughnesses, of course, by first of all grinding a pellet the end face smooth, but then we could roughen it up by just normal sandpaper and re-measure it to see how the roughness was affected. We could vary the roughness. We could vary the pressure between the pellet and the probes, because everything was set up in a metallurgical press.
Yes.
And have the pressure around this value that would experience during irradiation, which is 2,000 pounds.
Right.
And we automatically we obtained, by passing the heat down the column, the top surface would be hotter than the bottom surface, so we had two different temperatures. So that was useful too.
Yes, yes.
The first time we were just interested in roughness, and we did all these measurements in vacuum. The cover went over the assembly, and we did everything in vacuum. So that was simple. But then we got on to introducing gases into the vessel to simulate fission gases like xenon, krypton. We also put in useful stuff like hydrogen, because we thought if hydrogen was there, that would be a really good conductor. But then that didn't quite work out because we got involved with accommodation. And if the gas in that gap is, say it's hydrogen, low molecular weight, comes into contact with a surface like UO2 or even zircaloy with a high molecular weight,
Yes.
the gas is just not accommodated with respect to transfer of energy. It's better if the
Pardon me.
molecular weight of the gas is similar to the surface which is trying to extract heat from. So we got into the work of with gases. We got into the explanation why the heat transfer coefficients using hydrogen weren't as high or as good as we expected.
Yes.
And Archie
Pardon me.
Archie helped us a great deal in that respect. And what it does, because the gas doesn't assume the temperature of the surface it's against very easily, on either side of the gap, it effectively increases the gap distance. And accommodation coefficients we were able to give them a dimension in microinches as their effect on increasing the effectively the gap distance, or the gap width.
The gap width.
So
with surface roughness taken into account.
Archie helped us put together an equation which coped with pressure, roughness, what we thought the gas accommodation coefficients were, and so on, to come up with heat transfer coefficients which
Yes.
made sense. So that work went on for quite a while, because in those days we had to wait for the temperatures in our column to come to equilibrium. So we would start the run in the evening, come in the morning, and hope everything had settled down,
Right.
and that the pressure was still on, stuff like that. So it was a very slow process to get what we thought was good data. We were involved in thermometry, and thermocouples sometimes have a habit of losing their EMF slightly. So we had to be very careful about that aspect of it. We were trying to get the temperatures of these surfaces carefully.
Carefully, precisely measured, and
There's some very strange results. Maybe one result in vacuum, with just the surfaces pressed together, the heat transfer coefficients at low pressures were down here, and a little bit of pressure they zoomed up, and we can never understand that. But it happened.
But it happened.
You can't change the data. But that was the only run which looked a little different from the others, and I don't think we ever did explain it.
Well, that work formed the basis for the gap conductance modeling in CANDU fuel and in freestanding fuel.
Yeah, thanks to Archie, because he knew that we had to have numbers which could be used in modeling.
Yes.
He knew that. We were more concentrated on getting the numbers.
Getting the numbers, but then over time those were proven and in reactor experiments. And
Yes, so my daughter told me. She looked up she found a Ross and Stout reference somewhere. It was down in Egypt or some foreign country, and they effectively verified the numbers. Thank goodness.
Yes, well, I mean, my copy of the CANDU Fuel Engineering Manual at home on my bookshelf has the Ross-Stout gap conductance equation in there. in 70s, in the 1970s. Just a few of the coefficients were tweaked, but
Yeah.
based on in-reactor measurements. But
Well,
it stood the test of time, and it was used across the industry for many years, and still is. Yeah.
Yeah, well, I'm sure the data's good, but I have Archie Robertson to thank for that, because he knew the need for that equation
Yes.
rather than just
A correlation.
all of a sudden,
Yeah. So Alan, another area of research that you got involved in was neutron radiography.
Mm-hmm.
Can you tell us a bit about that and the experimental work and the modeling behind some of
Well, I
that?
was recruited for that by Jeff Chalder, who was in charge of our small group, looking at metal fuels, U3SI in particular. And in those days, they were aware that the fuel would swell. So to accommodate that swelling, they drilled a hole down the center of it. And neutron radiography would have the ability to penetrate the fuel and to see how the hole was closing up, for example.
Mm-hmm.
So he asked me to look after the neutron radiography at that stage. And that's how it really started. In fact, the first radiograph we took was a bird. And we wanted to show the muscles in the bird, because the muscles evidently contain more hydrogen than the rest of the bird.
Okay.
And it came out beautifully. Poor little bird was the first radiated specimens that we knew. Anyway.
Interesting. And the radiography was done in NRX?
NRX, we had a facility in NRX, and the beam of neutrons was extracted through the thermal column of the graphite thermal column of the reactor as a beam. In those days, the picture size was like 5 by 9. That's the biggest beam that was available. Most of the fuel elements which we were asked to radiograph were from the loop tests in NRX.
Yes.
Things that had misbehaved, and they wanted to have a good look at what had happened in the assembly. Later on, I managed to persuade the design people and operations people that the picture size should be increased to 20 inches, so we could cover the whole length of, for example, fuel elements from NPD, from the power reactors, which were all 19 inches long. And they did that very well. So we ended up with radiographs this long,
Okay.
6 inches across. So that result was interesting, because I was wondering about what would happen to the sharpness of the pictures, etc., if we did anything to the small beam that we were using. But it works okay. We didn't change the collimator, the hole in which the thermal neutrons enter. That wasn't changed. Just the length of the size of the collimator was increased by taking out some of the graphite of the column.
Okay, so just opened it up.
Just open it up, yeah. And they did that very well.
Interesting.
So we had to change our detection system to a bigger detection system. Instead of dysprosium films this long, sheets this long, they had to be that long, but they were available from the States, no problem. And Kodak gave us conveniently shaped film, single emulsion film, for transferring the dysprosium picture to film later. So there was no obstacle at all. The change was very smooth, thank goodness, because we were having a lot of elements for being radiographed coming all the time.
Mm-hmm.
We really became a service group. That was okay. But I got involved with the US again on standards. They're very hep on having a little picture in your radiograph which showed that you were using a truly thermoneutron beam. There wasn't a gamma picture, wasn't a gamma radiation picture, stuff like that. So they were developing standards, and Harold Berger, who was a father of neutron radiography in the States, and I got together, and a guy called Barton, John Barton, he was the top dog in this detection system. So we were kind of negotiating what standards should be relevant to pure, particularly pure radiation. And Berger wanted me to join a committee down in the National Bureau of Standards, but I was just too busy, and I had to say no. But it was that use of standards was, of course, very important to a lot of the workers. You had to have a standard. You had to have a reference in some corner of the picture which you can say, this is a thermoneutron radiograph,
Right.
not something else.
Right.
At the same time, we were looking at the behavior of hydrogen in affecting the zirconium alloy cladding, which would hydride.
Right.
If the cladding developed a leak, and the light water in our loops here would get in, and it would hydride the cladding in a little spot. When we got power reactor fuel, of course, that had been tested in heavy water,
Yes.
deuterium, and that is good and transparent. So we had to rely on anything they felt had failed. It would be stored underwater after radiation, but the light water would leak in. So we would see that leakage.
The signature of the leaked
It wasn't
hydrogen.
Yeah, we didn't use hydrogen.
Interesting, interesting. But you could pick up the hydrided material through radiography and show
Yeah,
how the defect
if it was
had progressed,
hydrogen.
or if
If it was deuterated, though, we just relied on spotting a light water getting in the hole.
Yes. Okay.
A little crude, but
Interesting.
it
Interesting.
was just almost just as effective.
Can you tell us, Alan, about interactions you had with W.B. Lewis?
Yes, that was very interesting, and I survived it. I don't know why, but I got interested in the gas puncture work being done in the shielded cells. I forget the name of the guy, but all kinds of elements, when elements were irradiated, they took the element and put it in a gas system, and they could drill a hole through the sheath and collect the gas given off.
Yes.
And I think, I mean, I was so far removed from that work at the time, I think they were trying to show that there was a knock-on effect, that the gas coming you would collect from the element was less than expected, depending on the burn-up of the element in the radiation, the temperature to be at, and so on and so forth.
Yeah.
So I collected the data together because they had irradiated powders, which have very high surface area. They had irradiated powdered granules and whole fuel elements and so on. But all this puncture data was sitting there. So I had a look at it and said, if you collect this data over a wide range of surface area and irradiation exposures, all the loop experiments, the elements were always gas punctured, and get it together, surely that will show that yes, the amount of gas you can suck out of a fuel element is less than you'd expect because of this knock-on process where the fast neutrons would strike a gas atom and knock it back into the lattice.
Implanted into the surroundings.
Yeah. It's called knock-on.
Yeah.
And so I don't know how Dr. Lewis got hold of me, but I had a phone call come up to my office. So I took all my data, and again, I was sure that I hadn't buggered things up by not understanding the data. I had a big sheet, all these experiments, and he seemed to accept it. He didn't say, oh, well, yes, yeah, he didn't say yes, but he didn't say no. So I was there about an hour and went over each radiation. He went over very detailed, and I understood that. He wanted to know that I had my facts right, and I knew that he was very enamored of knock-on, because if you had knock-on, then you wouldn't. This fission gas wouldn't be available to do other nasty things like distorting the fuel element.
Yeah.
And it did show it. And Ross McEwen at the time was writing a paper on pure behavior, and it got incorporated into that. But I have to just mention my work at Harwell.
Okay.
At the end of the heat transfer work, towards the end of it, I was asked to swap with a scientist from Harwell. He would come here and I would go there. I said, okay. So off we went as a family to Harwell, and I joined a Beryllia group, BEO, working on Beryllia. It was a self-contained building with its own workshop, its own showers, its own exhaust system, because of course Beryllia is a nasty animal,
Highly
medically.
toxic. Yeah.
But as I did with UO2, I had to put my knowledge of pressing the Beryllia powder into specimens, long specimens, short specimens, so on. So that took me a little while to get the technicians there to accept what I knew. But the problem with Beryllia, as far as I remember, was that it developed microcracks. The crystal system for Beryllia is hexagonal, and that didn't help. It would expand in one direction more than another, so the grains were separating, and tiny, tiny cracks were opening up between the grains. It's like a brick wall, and the mortar developing cracks. I thought, well, if I can get the samples vibrating at their natural frequency, I knew the Young's modulus elasticity is used to calculate that frequency. If I can get them vibrating, and like a bell ringing or ring, and then shut the power off and watch the decay of the sound, the ding, you know, and the cracks should affect that. It should get shorter and shorter if the more the cracks there are. And so the electronics people at Harwell very kindly built me a system. I had inch-long samples, rectangular samples, and I would paint the end with conducting cement, gold conducting cement, and they would be put the sample between two electrodes, and then the electronics would force the sample to vibrate. I would suspend the sample between two wires,
Yes.
so you just held it at its midpoint. So it was more or less free to do its own thing. And get it vibrating and shut the power off, and they would time the decay of the vibration. And sure enough, the irradiation, because it was causing little cracks, made the glass ding get shorter and shorter. And there again, I could show too that by taking these samples that were damaged and heating them to anneal that damage, that could be done, just like Wegener energy.
Right.
So when I left there, I was there 2 years and a bit, and my dad was dying. I tried to stay until he died, but that didn't work. When I left there, a technician I noticed was using the machine checking samples. So that was interesting.
Interesting.
Beryllia.
And that was in the late 70s, or?
60, oh, yes, I'm sorry. I just can't remember. I was only there 2 years, and I came
2
back
years, yeah.
to
Came back to Chalk River
To
after
Chalk
that
River,
exchange. And it was someone came from Harwell and worked here.
yeah, they did. They lived in our house, and we lived in their house.
Oh, so it was not just a workplace, but also living accommodation swap.
Yes. Unfortunately, the first house was terrible. So we moved from there into the Harwell village and rented a 100-year-old house, which was interesting. Much better place. We were given he lived in a prefab, what they called a prefab, and they were very poorly built because they built in a hurry, but there was a whole string of them by the site, which was very convenient to walk to work. But it wasn't near the schooling for the kids. So we moved down into the village, and they went to charming village school there, and we were able to ride horses and all kinds of stuff.
Interesting, interesting.
Then I came back to Chalk River and joined the Flute Lab, I guess, soon after that. They needed help.
And there,
Alan Jess was the leader in those days. And there was Alan Jess and a guy called Jim Cairns and a couple of attached staff from Argentina, I think. I can't remember. But about 8 technicians. And the Glovebox line was a self-contained production facility.
yes,
And you know what it's involved. And my job, as it soon developed, was to create a computer system to an accounting system for where everything was.
ah, okay,
Because the we were dealing with large quantities of uranium dioxide, sometimes plutonium dioxide, and you had to be aware of where everything was. You didn't want a criticality event.
Criticality.
So the system was called INMAX, INMACS,
Okay.
and Robin Poole of Electronics Branch, and his technician or cohort, Larry Anderson, and I created this accounting system. We had terminals in the lab, and I, being the system manager, had my own air-conditioned room and a computer, huge, great computer, made by digital equipment, and tried to make the use of it user-friendly. Like the process itself, you would receive material that would have to be batched.
Yes.
You'd have to enter its composition from chemical analysis, what that batch was, how many grams it was, what's its composition. Then that was moved to the spot where it would be pre-pressed and granulated, and then on to the press to be formed into green pellets. Well, that was very okay. That was one zone, as it were.
Yes.
But the actual composition of the UO2 changed, of course, to UO2 after sintering hydrogen. So there's a change in composition. So that had to be accounted for in the system. We had a composition file, so that had to be looked up, and the composition reverted to UO 2.0. After that, the pure pellets, after they were sintered, were put through a centerless grinder.
Yes.
In gloves.
In the glove box.
And of course, we collected the grindings in light water, and so the weight of the ground pellets had to be recorded, and the difference was what had been ground off, stuff like that.
Sure.
It all had to be managed by little programs in the INMAX system.
Yes.
Other than that, it wasn't a complicated process. You know, it was mixing, pre-pressing, pressing, grinding, and so on. So, but it had to be controlled so that we always knew where everything was.
Right. Including the residuals, I guess.
Including residuals.
right.
And we also created a burden account.
Yes.
We assumed that if we weighed something that weighed 100 grams, the balance might not be exactly right and might give us 99 grams. So there's a burden account created. If we weighed something like that, we would take a certain percentage and leave it in a burden account. And the only way that burden account could be zeroed was by do a physical inventory of the glove box system.
Correct.
Make sure there's nothing there.
A major clean out.
And then we could zero the burden account. That was
Right.
my responsibility as system manager. Stuff like that.
Interesting. Well, I didn't know that you were the author of the INMAS system. I know it's another connection between my career and yours in the sense that
Well,
probably in the late 80s, I was the MBA head in Building 375 and used to approve the gain losses
oh yes.
on INMAS out of the Flute Lab.
Well,
and some of
it's
the other
probably
labs,
greatly
so-
improved after I left. Because,
Well, it stood the test of time, Alan, so yeah.
um,
Interesting. Interesting.
People like um, Roger Chotter Jarvis was always interrogating us because he was very much aware of how mistakes can be made in computer systems and electrical failures and so forth. So he was a good watchdog over us at that time.
Interesting. Interesting.
I happen to be a member of the criticality panel, which assessed criticality concerns, and the patents committee, and they all seem to merge together.
Yes.
Uranium silicide, the metal fuel, was a bit of a problem with corrosion. It would not feel happy in high temperature, high pressure water. So we knew that from corrosion tests. So I don't know who decided, it wasn't me, I take no credit for it, but somebody thought about adding a little bit of aluminum to the mix. And we found out later because the deltizing process for the U3SI, where you're trying to get uranium to combine with silicon, always left over a little bit of uranium, and the aluminum which you added would mop that up. The result was that the corrosion behavior was transformed. Instead of the U3SI after a test looking at the rusty knives of your mother's kitchen drawer many years ago, it would come out shining like stainless steel. And the corrosion rate went down by at least 3 orders of magnitude. So I decided we should patent this because U3SI was, and U3SIAL was of great interest to research reactors. And so we did that. So I got a patent.
Okay.
And I got paid $11. that was just great. So, but I was just amazed, which just a small amount of aluminum transformed the metal pure rod into a shiny object. But there was one trouble: was it wouldn't respond to leak tests in the reactor. If you drill a hole in the sheath and then put it in the reactor, it would just sit there.
You couldn't tell if it was leaking. Yeah, I know.
You can't have everything.
Kind of, but much better problem to have. Than,
yes, exactly.
Corrosion. Yeah. Well, that's another interesting fact I wasn't aware of. So.
But you see, the chemical engineering branch had an autoclave in which we could put the corrosion samples in a stainless steel bucket, hang them in there, and expose them to the high pressure, high temperature water for an hour, and then take the samples out and measure them, weigh any weight loss and stuff like that. They just were so helpful, you know. Everybody was helpful. I was very, very lucky. Very, very lucky.
Well, it sounds like it was definitely an interesting time to work and solve problems and develop techniques.
Our level of knowledge was, I won't say low, but it needed boosting a lot. And the Americans, as I say, were involved in submarine reactor fuel, and they had different problems. And they were certainly involved in knowing the non-stoichiometry nature of UO2, and how the U409 phase would appear in metallography, stuff like that. They did very nice work.
Interesting.
But it's just one thing after another, it seemed. That's why I had to say no to the National Bureau of Standards to go down and work there on their committee, if it was only one day a week.
You know, when I started as a fuel engineer in early 80s, in the fuel engineering branch. Dick Stout was there and drilling.
Still drilling away.
And other, working
other
with
things.
Specialty thermocouples and instrumentation
cladding,
inside the cladding, outside the cladding.
Yeah.
And metallography but one of my first jobs was looking into uranium properties and all the oxides of uranium. And so I went to the book that had your chapter in it on
UO2.
Jack Bell's UO2, and anyway.
It was a shame that we couldn't use uranium with its high uranium density. About 19, wasn't it? instead of a UO2 down less than 10 or
Oh, right.
just over 10.
The metal versus the oxide.
Yeah, that was a big
yeah.
change in core design.
Yes. Yeah. Yeah. You've been retired for
Yeah, 36 years.
36 years.
Incredible. Amazing I can remember anything.
So, your hobbies and interest in post-retirement?
Well, when I first retired, I thought you better start looking after dogs and houses and cats. So I did that. But a very rough dog pulled my arm one day and pulled the muscle here. So at the time I was trying to play golf, and that really didn't help. So I took up golf and persisted with golf, and I enjoyed that. And we had a nice garden. I enjoyed gardening. And I had a wife who, my second wife at that stage, who really agreed with me retiring because it was a financial incentive from the company. We had the buyout that 1 year.
Okay.
And she agreed with me that it would be a good thing because it was getting pretty hectic at work. We, ever since Atomic Energy, to get funding from the government, had to be perceived as a business. Then we had to have all kinds of meetings for business plans, milestone charts, etc., etc. And some people thrive on that, but I didn't particularly thrive on it. It's just a big nuisance because it took me away from what I'm supposed to be doing.
Sure.
And the meetings were not short meetings. Anyway, and I just developed skin rashes, I guess because of stress. But anyway, I retired, and my wife was happy, and we had 10 very happy years of gardening and golf and cross-country skiing. And I would recommend anybody not to, well, we should be told, don't worry about finances, you'll manage. It's something not to worry about. Of course, you can't really be too convincing until people have experienced it, I know.
Yes.
But we had, as I say, 10 good years of, and we used to go down south for a couple of months and swim in the ocean and in Florida. And later on, when my wife's back started not being able to cope with the 1,900-mile drive to Naples in Florida, we stopped off at Myrtle Beach. And we really enjoyed Myrtle Beach. And it was only 1,100 miles from here. So we enjoyed Myrtle Beach for a few years, but then her Alzheimer's set in, and that was the end of that phase. So after that, I seemed to become a caregiver because I took care of her, and my next wife developed dementia, took care of her, and I'm not really looking for any new wife, but I don't know what's going to happen. I'm the kiss of death.
Well, Alan, you've had an interesting and wonderful career and post-retirement.
Well, I was very lucky. I must say one thing, that Chalk River, we had so much available. We had chemical analysis laboratories, Floyd Miller, that group, they would do chemical analysis for us. We had mass spectrometry analysis, we had electron microscopes, we had optical microscopes, we had our own machine shop, we had the main machine shop for bigger stuff, and there was so much available to help us. It's incredible. I don't know what it's like now, but when I was there, and we had no budget. Can you imagine?
Right.
The administrative officer of the division would handle the budget part. So if we wanted say a metal balance, which was the priciest one on the market,
Yes.
but we needed it for its rigidity, its life, because it's going to be in a glove box a long while, and its accuracy, then we would give that reason for it, and we would get it. It was no problem in obtaining stuff to do research with.
Yes.
In those days.
Yes.
It was a paradise place, really, in retrospect.
And there were people in the procurement groups whose job it was to
procure.
obtain all that material
Yeah.
for you. I remember.
Yeah, we used a big catalog, a great big thick catalog, to all the small stuff, like those springs I mentioned, quartz springs. I was very worried that they wouldn't get here in one piece, but they just put them in a tube, filled the tube with water, and put the lid on and sent them like that. The water was a perfect cushion for this very delicate spring. Amazing.
Interesting, interesting.
But I have Atomic Energy to thank for those years, because they really supported the effort to get good data, good science data. There was no fudging of stuff.
Mm-hmm.
And you were able to do that because of their support. So I'm very, very lucky.
Well, you've certainly had an interesting career.
Well,
So it's
varied, many hats.
It's been a pleasure to hear about it. So, thank you very much.
Well, thank you, thank you. A pleasure to try and remember it all.